Hello everyone. Let us discuss digital modulation techniques, and under digital modulation techniques I will discuss today what is frequency shift keying. In frequency shift keying, the message signal will be modulated onto the carrier, and the parameter that will change according to the message signal is the frequency in this case. So the amplitude of the modulated signal, now XMT is actually the modulated signal, the amplitude will remain constant, and cos 2 pi f naught is the carrier frequency, so plus 2 pi delta f m t, small m t. Now this delta f is the frequency changes that will take place according to what digital stream is to be transmitted. For example, for m equal to 0, the frequency will be for f equal to f naught. Now, for m equal to 1, the frequency will be f naught plus delta f. That means this delta frequency will be added into the carrier frequency corresponding to m equal to 1. And what is capital M? The capital M is the dimension of this frequency shift keying. That means how many bits are to be represented, how many signals of different frequencies can be transmitted onto the channel. These different signals are representing the combination of bits. All right. Now, for example, if there is a binary FSK, in that case, 0 and 1 is to be transmitted within one symbol period. And in that case, 1 will be transmitted with a signal of certain frequency, let us say f naught, and 0 will be transmitted onto the channel with a frequency f naught plus delta f. So, when the signal is received at the receiver, two frequencies can distinguish between whether 1 was transmitted or 0 was transmitted. Right. So, what are the frequency available for frequency shift keying? So, that will depend on delta f. What delta f you choose, that will determine how much frequency shifts you will get from the carrier frequency, right, to represent the digital bit string. There can be binary FSK. There can be four array FSK, or in general it can be M array FSK, depending on how many bits are to be transmitted during one symbol period. Correct. So small m will vary from 0 to capital M minus 1, and this small t is a variable which is of course varying from 0 to capital T, where capital T is the symbol period. Now this XMT can be expressed as SMT, right? E to the power j2 pi f naught t, and where SMT I can denote it to which is the signal, basic message signal. So I can express it to be where SMT is under root 2 e by capital T e to the power j2 pi small m delta f t, right? So basically what is done in this expression is that this cos 2 pi f naught t is replaced with the Euler's expression, and we are taking the real part of that. So that will be equal to this expression only. Once you open up this e to the power j2 pi f naught t, right, and this factor, so you will get this cos. The argument will be the same once you take the real part of the of this expression, where SMT is given by this expression representing j e to the power j2 pi m delta f t, right? So that means in frequency shift keying, what we are doing is that we are using the frequency as a parameter to represent different combinations of bits to be transmitted onto the channel. Now let's see the inner product, because let us see, we have this modulated signal, right? Now let us look at the inner product of the two different signals corresponding to different m and n. So let us the inner product of xmt comma xnt, it will be given by, we will take the values of xmt, where here I will use the m as the parameter corresponding to xmt, and here I will use n as the parameter corresponding to x and t, because we are taking the inner product of these two, right? So inner product will be equal to, because the two inner products will multiply, so under root 2 e by 2 will become 2 e by 2. Integral will be from 0 to capital T. So this particular term will be for xmt, and this particular term will be for x of nt. Now, if you multiply these two terms and use the trigonometric formula, you will be able to get this equation, which is e by t, because 2 cos a cos b is equal to cos a plus b plus cos a minus b. So that trigonometric formula you can use here. So you will get e by t 0 to capital T cos of 2 f naught plus m plus n delta f t plus cos of 2 pi m minus n delta f t dt. Right. Of course, the integral variable will remain time. Now, look at the first term. The first term is actually m plus n. The frequency of the first term is very high, because this is addition of the delta f and it is being added into the carrier frequency, which is twice even. So what will happen is the frequency of this signal is very high, and that means its period will be very small. Since the frequency is high, of course the period will be very small, and which leads to very small area under the curve. So therefore um, average is 0 for this part. So this part is actually representing 0, because the average value, once you will take the integral from 0 to capital T, and you know that the frequency is very high, and the period of this part will be very small, so average is almost 0. So we can neglect this part, and the rest of the part will be 2 pi m minus n e by t 0 to capital T cos of 2 pi m minus n delta f t dt. Right. Now, since that's what I'm since 2 f naught plus m plus delta n delta f is very greater than 1 by t, as I have just tried to explain to you, so we can neglect this part. Now you take the integral, now you solve this integral, and you will find that it will be e by t sine of 2 pi m minus n delta f t 2 pi m minus n delta f, which is actually a sinc function, right? You can just do the manipulation here, and you can put capital T, you can multiply and divide the expression with capital T, so you will get a sinc function here. So the resultant expression will be capital E sinc of 2t delta f m minus n. Now we want to see for what delta f the two signals become orthogonal, because once the two frequency signals are orthogonal to each other, so detection will help in the detection of the signal, that the receiver will be it will be very convenient for the receiver to detect once the two frequency signals are orthogonal to each other. Now we want to see when this, because what we are doing with this solution is that we are trying to find out the inner product of the two signals. Now when we want to see when this inner product will go to 0. Now if you see this expression, this inner product will go to 0, will be for when this inner product is equal to e into sinc of 2t delta f when m minus n is equal to 1. Right. So in that case, this so if delta f for m minus n equal to 1, and if delta f is equal to 1 by 2t, right, this dot product will go to 0. So when delta f is equal to 1 by 2t, this function will go to 0. This is 0 here, this is 0 here, at the multiples of 1 by 2t. So at 1 minus 1 by t, and even at 1 by t, it will go to 0. So what happens is this dot product will go to 0 when delta f is a multiple of 1 by 2t, and the two signals will be orthogonal to each other. Now this is the condition, uh, and this waveform is symmetric. Now the dot product is 0 if delta f is a multiple of 1 by 2t. So this is the condition for orthogonality, which will be used in frequency shift keying. That means the delta f that we will select, the frequency shift that we will select, from the carrier frequency, it should be a multiple of 1 by 2t. Then we have mathematically proven that the two signals will remain orthogonal to each other, and for any m and n, FSK signal set is orthogonal to each other if 1 by 2t divides the delta f. If one, what is the meaning of this 1 by 2? If delta f is being divided, 1 by 2t is the factor to divide this delta f frequency. Delta f is the frequency shifts that we will take to design a frequency shifting signal set, FSK signal set. That means what should be the frequency shift from the carrier frequency, so that the signals that result from designing the signal set should be orthogonal to each other. And the condition is that the 1 by 2t is the factor which should divide the delta f axis. So at those points only we can select the frequencies to to increase the number of points in the signal set, right? Now here also we define a orthonormal basis function, right? In this using this basis function, we will be representing all the signal points in the signal set. Now phi I t is the orthonormal vector, so it will be 1 over, let us define this, 1 over under root e xit. So that means all the signals can be expressed. So we define this basis function, and here if you will see, all the signal set can be expressed in terms of this phi it, which is a unit energy signal basically, right? And value is given by this, so it is under root of e phi it. Phi it I am selecting it to be 1 over under root e I xit. So of course m will vary from 0 to capital M minus 1. Let us say for capital M equal to 3, that means we are selecting three basis functions. Three basis function, because I is the index to represent the basis function. We select the three basis functions. So it will be equal to phi naught t, phi 1 t, and phi 2 t. So this is the orthonormal basis. And I can express my xit, which is the actual signal, equal to under root of e phi I t, right? So it will be along one, because the basis functions will be orthogonal to each other. This is the orthonormal vector we are trying to use. So phi 1 t, phi 0 t will be orthogonal to phi 1 t and phi 2 t. So what are the points here? You will see that you can find from using um, here also, that it will be 0 under root e comma 0, right? If you find out the distance between the points, it will be this xit is equal to corresponding to phi 0 t, right? So what is the, because phi it will be a unit energy, so phi it will be a unit energy here, that means its value will be equal to 1. So this point will be there, so its value will be under root e 0 comma 0. The coordinates of this point will be under root e 0 comma 0. Coordinates of phi 1 t, the coordinates of the second point will be 0 under root e comma 0 and 0 0 under root e. Now if you try to find out the distance between the 2 points, you will find that the distance is under root 2e. If you will use this coordinate and this coordinate, you will see that the distance is under root 2e. And for any arbitrary value of capital M, because in the previous example I am using the value of M to be equal to 3, and I found out that the coordinates of the different signal points are 0 0 under root e, right? So this is this axis is represented by phi naught t, this axis is represented by phi 1 t and phi 2. These are the basis functions, and if I try to find out the distance between the 2 points, it will be under root 2e. Now, for any arbitrary point, I can say that the coordinates of the points of the signal points will be x naught will be under root t comma 0, and x1 will be 0 under root t, and all zeros rest. Xm minus 1 will be 0 comma 0 comma 0, and the last point, which is the m minus 1th point, will be under root e. Now let us discuss the properties of the orthogonal FSK. All signal points have same energy. All signal points have same energy. So what are the signal points? Under root e 0 comma 0, 0 under root e comma 0, 0 comma 0 under root e. So they represent the same energy, right? Constant, though this is also a constant energy modulation, as was the case with the phase shift keying. But here this is important point. Here capital M equal to n. If you see, when you select m equal to 3, you get 3 signal points, but it was not the case in the what is capital N representing? Capital N is representing the number of basis functions. So when m equal to 3, how many basis functions are required? 3 basis functions are required. But in the case of phase shift keying, if the value of capital M is, let's say, 8, how many basis functions are required? 2 basis functions are required to represent the phase, to represent the constellation diagram, using constellation diagram in terms of the phase, um, right? So here the number of signal points will be equal to the number of levels that we are uh, number of, I mean, the signal points that we are using will be equal to the dimensionality of the signal set. Capital N represents the dimensionality. In the case of phase shift, in the case of ASK, what was the dimensionality? Dimensionality was 1. In the case of phase shift keying, what was the dimensionality? It was 2, because 2 basis functions we were using. In the case of QAM, what was the dimensionality? Again, it was 2. But in the case of FSK, it depends on the number of signal points. Number of signal points is actually equal to the number of dimensionality. That means the number of as the dimension of the signal space. So number of points is same as the dimension of the signal space. Bandwidth. So therefore, if the dimensionality is bandwidth increases proportional to m. Why it is so? Because if the number of points are increasing, because every point is to be represented with a delta shift, a delta f shift added to the carrier frequency. So as you are increasing the number of points, of course the bandwidth, you would require larger bandwidth to accommodate all the signal points. But in other modulation schemes, as you increase m, as you increase the number of signal points, the bandwidth does not increase. But the advantage is, of course, that the signal points will be orthogonal to each other. Energy and minimum distance both can be kept constant while increasing the number of points, but compromise bandwidth. So this is the advantage in the FSK. We can keep the energy and minimum distance constant while increasing the number of points, but of course it will require more bandwidth in case of frequency shift keying. Now the question is that how to do the demodulation. Uh, how to do the demodulation actually is that what I'm trying to do, what I will do now is that I will try to design demodulator or detection or a receiver kind of circuit which is independent of any particular modulation scheme. So it can be either pulse amplitude modulation, or it can be pulse shift key, phase shift keying, quadrature amplitude modulation, frequency shift keying. So the receiver that I will design here will be independent of the type of modulation scheme, right? So in that way, I will design a generic kind of receiver that I will cover. I will cover this slide in my next lecture. So I, up to this point, I finish with the frequency shift keying and its various properties. And in the next lecture, I will describe about the how about describe about the procedure to design correlation receiver and match filter receiver for which will be, of course, independent of any modulation scheme you are using. So that structure of the receiver can be used to detect or to demodulate the signals. Thank you.